as span and independence, right? Linear independence and things like that. So this type of a description of a subspace is at more of a condition type. Would you agree? Subspace is described as using the condition. All right. Here's our space, collection of everything that satisfies this. That's how these are formulated, right? Span is a different idea. It's namely geometrically they're calling this one a parameterization. Remember in Calc 3, you give a surface and they parameterize that surface using a parameter S and T. Lines are parameterized using that. That's a geometric term, and in algebra we usually call those the generators. That's a general algebraic term, but linear algebra they call it's a span and linear combination and things like that. So you first look at it here, figure out the generator. This is a space there, right? One plane in three-dimensional space. Figure out the generator that generates, or parameterization. Parameterization is easiest to think about. If you have to parameterize it with a 2 free variable, 3 free variable, and you can do that. How would you approach that that one there? X minus 2y plus 3z. It's given by condition. How would you parameterize each point in there? How many free variables do you think it's going to have? 3, right? 3 things are all free here. X is free, Y is free, and Z is free. If they're really free, how can they satisfy this condition? No way, right? I can just put anything in here if it's free, and likely it's not going to be 0, right? So how many? 2 free variable. It's your choice. I'm going to stick in this 2, that 2, things like that. But X is very nice, 1 times, so that's easy to isolate. So you choose a free variable, y equals s, and z equals t. Those are going to be my complete. You can just put anything s and t, right? Correct? And then do what? You solve for x. That is 2y minus 3z. Correct? This is written as what? 2 times s minus 3 times t. Is that right? So let's see how it's parameterized. X is parameterized by 2s minus 3t. Y is parameterized how? With a complete free variable s. Z is parameterized by complete free variable t. This is called parameterization in a calculus level and analysis. All right, let's enter linear algebra. So how do we describe this space in linear algebra? We want generators, right? What are the generators what are the things in this space? Column vectors, right? We want to find the column vectors that generate these guys, correct? So we enter x, y, z. Those are what we're looking at, and this guy satisfies this condition there, right? And we analyze this. X is going to be 2s minus 3t, and y is going to be s itself, z is going to be t itself. So if you just plug in any s and t random here, this will sit inside that plane. Conversely, any point you pick in that plane will be described like this, which is not properly argued here because of the direction of this implication. But if you're going backward, obviously it's true. So these are reversible arguments there. We completely describe it. You see vectors here? So what do we do when you see s and s? You collect them to s0. You see that? And what is the operation? Your plus, right? You collect negative 3t, 0t. See that? And then you pull out all of them. 2. What is it? 2, 1, 0. Is that correct? And what about the other one? T, negative 3, 0, 1. What just happened? Random point xyz is linear combination of which two vectors? 2, 1, 0, negative 3, 0, 1. Isn't that a span, right? And you can check these are actually linearly independent. Fantastic. spanned by linearly independent vectors. That's the whole goal of that thing. All right, so this subspace we're looking at is now a span of what two vectors? 2, 1, 0, negative 3, 0, 1. Is that right? Yeah. That was something you guys read about yesterday, the meaning of a span. All right. Any question about this? So I think I thought I have prepared this. Oh, there it is. Example. This is one equation, right? So I'm going to give you 4 variable equation and three things. So here's a 4 variable, another example. 4 variables and 3 equations. Can you imagine that? So W, X, and Y, and Z. Those are the variables. And how many equations did we have before? 1 equations, right? So here I have 4 variable and 3 equations involved. You're going to write those down like that. 1 equation and 2 and 3 equation, all set equal to what number? 0, 0, 0. Such that is a subspace. If you put different number, it's not going to be a subspace. Okay? It has to be subspace like that. Now, going back to the very first and second class of your first linear algebra course, what do we do to this guy? Elimination, reduction, row operation. You're not going to do any of those. That's good news. We're just going to rely on the computer. Just reduce it. I'm going to give you some nasty giant equation, and then you're going to use your calculator and get this one. So what do you get out of the row reduction? So we focus on coefficient there, right? So we're going to have 1, 0. And this is an example, right? Just to help you to figure out. And it happens 0, 0, 0 there. Okay? Suppose this happened. What is the name of this form? I think it's called echelon form. Something like that. There's a reduced echelon form. Remember reduced echelon form? Yeah. Reduced echelon form goes like this. If you look at it like this, W is all multiplied here, right? X is multiplied here, Y is multiplied, and Z is multiplied here. That's the structure. And this multiplied, so these two are free, 3 and 2 are free. You can put anything there. This is X variable, right? X is going to be solved by the other two, so it's not free. So this location, there's a unique location there, right? First non-zero term in each row. That variable is not free because it's going to be solved by the other one. I think this is called a pivot position in that thing. How about here? That's the pivot position, right? Those pivot position correspond to independent variable. And position in here, 3 and 2, correspond to Y and Z, is never pivot position. So they are going to be what? Completely independent variables, right? So you start with what? Y equals S, and Z equals T, right? And solve for X and Y there. This is not reduced echelon form. Reduced echelon form goes like this. First, you have to change that 2 to 1 by dividing the 2. Each of the pivot position, once you change that to 1, you can clear whatever is above that pivot position by multiplying this one, negative 1 here, and add it there. You see this 1 is knocked down? Multiply negative 1 here, and add it to the first row. It knocks down that 1. You can see because of the non-zero there, you can knock down anything that's above. And because of the 0, it's not going to affect any of those that's above there. You can further reduce. So above here is completely 0. Above the pivot position, they're completely 0. That would have even more advantage when you write down the generators of the span. Okay? So why don't we spend just 30 seconds or so using the same idea here, same idea to write down eventual goal is that you consider w, x, y, z all in terms of what variable? S and t. Okay? But you can imagine in between 2 and 1, is there jump in that pivot position? No, it's right next to each other, right? So it did not introduce further free variable. But if there's additional gap between the pivot position, they all correspond to free variable, right? So I want you to solve completely w, x, and y, and z in terms of s and t, which is completely free, and replace those things with s and t here, and see if you can separate it like this. From there, you discover the generator. I thought it's like a 30-second exercise, right? So let's do that. All right, I got 3, negative 3, 1, 0, and 1, negative 2, 0, 1 by separating like this. Is that okay? And you can see, because this 1 is also involved, this calculation got a little bit of work. Imagine if this is a 0 and there is no involvement of x in there, so it is fairly simple. Right? Because x kicking in, that is going in there complicated. So if you clear that up above first, this parameterization a lot faster and cleaner shape is like separating each other completely, much nicer way. So that here span of this vector and that vector is the answer. That's the generator. Okay. And this is one particular method relying on one particular form of echelon form. I was actually wrong. It was 2. W was there, wasn't it? Yeah. So it has to be divided by 2 further. So it's divided by 2. That's divided by 2 here, and t over there is divided by 2. Is that right? Yeah. So there's over 2 is involved. So that's if you don't like 2, you can pull out the 2 and shove it inside s. You can pull out the 2 and shove it inside the t. But that you have to multiply everything by 2 as well. If you want to deal with integer coordinates, that's not necessary. So that's a span. It's opposite idea. It's not conditioned. We want to describe a necessary vector to generate the whole thing. That's the idea of a span. Second example. Any question about this one? This is something you've learned already. So here's the second one. Is this polynomial of polynomial f is coming from where? Polynomial with a q coefficient. Let's say f of 2 is a 0, and the degree of f is less than or equal to 3, right? Any idea how to approach it? Number one idea, I think, is usual approach you can do is that, okay, how is f of x looks like in here? Degree less than or equal to 3. You go a plus bx plus c x squared and plus dx cubed, right? All the polynomials at degree less than or equal to 3 looks like this. Are we allowing d to be 0? Yes, it can be less than the degree. So any real number you plug in a, b, c will be inside it here. So how about the condition f of 2 equals 0? You plug in 2 in there, so this can be 0, a plus 2b, 3, 4, c, a, d, right? Those free a, b, c now has a constraint, which is this one, right? Yes. Any other question? Yeah, that came from there. All right. So how about t? Who wants to collect that? Negative 4, right? And x squared, that's right here. And there's a t. Correct? How about this polynomial, x squared minus 4? That works, right? That works. How about u? Negative 8 plus x cubed, right? Like that. So this is one function vector. There's a force vector, there's a column vector, and what is the most important vector in this course? function vector. Vector that itself is a function, right? Space of functions. So that's the function scalar multiple, function scalar multiple, function scalar multiple, right? So what we just looked at here is that this thing, f, f of 2 equals 0 and degree of f less than or equal to 3 is now span of what vectors? X minus 2. Do you see that? X minus 2 is a function, is a vector. Scalar multiple. What is the other one? X squared minus 4, right? What is the other one? X cubed minus 8. Now this guy is generated by how many vectors? 3 vectors, right? Good question is that, can somebody come up with the even clever idea to can generate down to 2 vectors, right? 3 vectors, things like that. And that's this dimension theory. All right? Let me say one more thing and I'll stop. Alternative approach is that if you have f of x, knowing that f of 2 equals 0, you can divide this any given f of x. So let's say f of x from that space that we call the w here. Then what you can do algebraically is that you can divide f of x by x minus 2. Long division. And what happens? You have quotient, right? But you have remainder in the long division, right? What do you do with the remainder when you make this identity like that? You add that remainder there. Correct? If you do the long division, any polynomial, 2015 degree, you divide it by x minus 2, you have a quotient up there, you have a remainder down there. Mathematical will do it for you. And then it goes into like this is identity. Okay? What is the choice of Rx in here? It's a polynomial of degree less than x minus 2. What is it? Degree of R here? It's a 0. What kind of polynomial has a degree R 0? Constant polynomial, correct? So this is really just a constant R. But if you plug in x minus 2, x equals 2, what is supposed to happen? 0, right? If you plug in x equals 2, that's a 0, but here doesn't change. So it should be 0. So further you can say f of x must have a factor of x minus 2 and qx completely free, right? Plus 0. Any polynomial in here must be in that shape. See if q of x is free in x minus 2. What kind of polynomial can you stick in here? Any polynomial degree less than or equal to 2. So they're all together degree 3. So I go a plus bx plus cx squared. No matter what you plug in there, this is going to satisfy our conditions, right? And then now you expand it. A times x minus 2, we recover that, right? B times what this time? X squared minus 2x. See that if you multiply here to that. And c plus x cubed minus 2x squared, right? Now exactly the same space w is now written in different generator, right? What is the first generator? X minus 2 is the second generator. X squared minus 2x, the third generator. X cubed minus 2x squared, right? The same space has a slightly different generator. All of this vanishes at x equals 2. And there's no unique choice of spanning generators, right? But there's a unique number, the minimal number, of course. And that is something interesting. And these are actually the minimal number. You can't go down less than 3. This is a minimal number.